Okay, so I just sent out the guide for test number 2 earlier this morning. You can take a look, but that should be very consistent with what we set on Monday. Okay, so assignment number 2 will be due, I believe tonight, 11:55 p.m. Just make sure you submit in time. Tomorrow I'll release the solution. I might be slightly delayed on the written part for the solution, but I'll definitely give you the programming part first. You can definitely start looking at the solution for the programming part. And then I'll try to really by the end of tomorrow, or very early, first thing on Friday, I'll give you the written part as well. So we're gonna meet in person on Friday, tutorial session, and then we're gonna look at the solution, some highlights. I don't think there will be many things we're gonna say in 100% detail, but maybe especially for the proof, for the Dijkstra algorithm, do your best, see what you can achieve before the submission deadline. I'm gonna do some highlights together with you, just talk about induction again. And then if there's any, okay, so I don't think today I will be able to leave any extra time for Q&A. So in that case, I can potentially make 1 hour or so before the tutorial session on Friday. So if you want to drop by my office, it's like an extended office hour just for you guys. If you want to drop by to ask some questions, you're welcome to. I'll confirm that, okay? So tentatively, it could be maybe from 2:30 to 3:30, right? So after that, you can still take a break, okay? I'll confirm. So today, we're just gonna finish off some stuff. So you can definitely finish going over your material for test number 2. Any questions? Yes?
So is the 1 hour on Friday or Thursday?
You mean the office hour, right? Friday. Yeah, Thursday will be difficult because I got kind of back-to-back classes, yeah, in the afternoon, yeah. Yep, for sure, Friday. All right. Right, let's do a recap from last time. All right, so last time we did a little bit diversion to priority queue because to really analyze the running time for Dijkstra algorithm, we have to know about what's the efficient way of implementing priority queue, which will be using a heap. So that's why I want to talk about this lecture first. Maybe something you have already learned from 2101, but that's okay. We can just revisit the ideas. I think it doesn't hurt to really brush up this kind of very important concept. So what I want to say, just remind again about priority queue. We assume that in this case, it's a minimum key priority queue. If I have to talk about like a maximum key priority queue in the exam or in the test, I'll let you know explicitly, but things will just be done symmetrically, okay? So we assume that the minimum key value will represent the highest priority, which should be chosen first. In the case of the Dijkstra algorithm, you want to choose the capital D value that's the minimum, which means has the highest priority. And it is okay to have duplicate value for the keys. We are not really using the keys in the priority queue to identify what's for searching purpose, not really. It is the case for binary search tree, but not for priority queue or for the heaps. So the keys value are just for priority value, which can be duplicated, okay? And you want to make some comparison with the regular FIVO queue, first in, first out, and together with priority queue, right? Just make some comparison, right? Okay, and then we talk about just about the row of the key, right? Exactly what I just said. And then we talk about the heap. So there are 2 properties that a heap must satisfy. Think about heap is more like a special case for binary tree. In order for a binary tree to be a heap, there's got to be 2 properties. It's got to be satisfied. Number 1 is about structural property. Number 2 is about relational property. So we started with the structural property. And the structural property said the binary tree must be complete. Visually, it's very easy to see whether or not the tree is complete. Basically, got the tree completely full until the second last level, until and including. And then in the final level here, you must have at least 1 node as a minimum. Maximum, you can have all the nodes, which will be 2 to the power of h, where h is the height of the tree. Okay, so you can definitely go over about the geometric sequence. And so for Monday, it is possible I may kind of ask you to maybe do some simple calculation according to the height of the tree. No calculator, so don't worry, I wouldn't give you a number that's too big, right? So if you know at least how to calculate, for example, 2 to the power of 10, I'm pretty sure you know, right? Things like that, right? Nothing very big. So no calculator, but it should be doable, okay? So you want to really revisit about the bullet point definition in the slides. I wouldn't repeat that. You can take a look. The way I presented the complete binary tree from Monday, we'll just go over bullet point by bullet point and see the correspondence in the diagram. You can revisit that part. That'll be very helpful. And there's another notion about full binary tree, in which case you will be just the maximum case at the final level, the bottom level. Okay. Okay. And then, yeah, geometric sequence. You may want to revisit this one here. Actually, we derived the formula back in the kind of very beginning of the semester when we did the dynamic array analysis. Okay. So structural property, something also very important. We didn't really derive the formula, but we know that, so this is a maximum case for the number of nodes in the complete binary tree, which means it got completely full right here. So that'll be the number. And then you can simply rearrange the term a little bit. For example, you can say, given this, if I try to rearrange the term, I can say 2 to the h plus 1, move the minus 1 to here, so that'll be equal to n plus 1. And then you can somehow take the log of both sides, right? In that way, you're going to get h plus 1 equals log n plus 1, right? Very easy to do, rearranging the term. And then we can somehow show that h itself, in the maximum case, will be big O of log n. It's a very important property here to know that in the case of the heap, because it satisfies the structural property being complete, so guaranteed, the maximum height you can get for a heap will be log n. So we're going to do insertion and deletion today. Both of them will be upper bounded by log n. Okay, it's going to be very important to see that. Okay. And you may also want to compare about the heights for self-balancing binary search tree. We'll talk about the height balance property, right? You want to see that too. Okay. Any questions about structural property? Okay, I think this one here is just about revisiting about the property of binary tree. Okay. And then we talk about relational property. Okay. This is something a little bit trickier to really get right. That's why we're going to do exercises today together about insertion and deletion. So property number 1. So any leaf to root path should really give you non-ascending order, which means you have to strictly decreasing the key value, You have to strictly decreasing the key value, for example, from 16 to 15 is decreasing. It's also possible you may have 15 again. It's okay to have the same key because we said keys can be duplicated. So that's why I said non-ascending. I didn't just say descending. Okay, there's a difference there. Just remember, whenever we want to compare, the child key value must be larger than or equal to the parent key value. That's the main principle to remember when you apply the principle for insertion deletion. We'll see very soon. And the minimum key is exactly at the root. So to really find out the minimum key value or the highest priority for the heap, you just go to the root, just find it. If you only want to get what the key value is for the minimum, you can just get it right away from the root. So it's a constant time operation. However, if you somehow want to remove this root, it's going to be trickier, right? Because you cannot just remove it. Otherwise, you just got 2 orphan trees without any root. You got to do some magic. Well, I wouldn't say magic. You got to do some massaging there to really reshape the tree. That's something we'll see, okay? And we talk about just different examples for heap. So just remember, in order to be a heap, you got to be both complete and also satisfy the heap order property. Okay, child key larger than or equal to the parent key. Okay, any questions about heap? Okay, let's now do insertion and deletion, right? Example. Okay. We wouldn't do any proof about why insertion and deletion are just simply correct. We wouldn't do that. However, there might be some, I'll try to see if along the way, maybe I can remind you something for you to think about. It's actually quite not difficult to really justify. Okay, there's certain steps you got to watch out for. Okay, just before that, we're going to do insertion followed by deletion. Okay, we'll start with the insertion. Before that, let me show you quickly the slides just to see where we are. So for this lecture series here about priority queue, so there are 3 main operations. If you just want to get a minimum, it's going to be big O of 1, which I just explained. Very efficient operation, cheap. And when you do insertion and also to do deletion, it turns out the running time, as we'll see, is going to be proportional to the height of the tree. So you can say big O of h. However, since the heap satisfies the structural property, it's a complete binary tree. Guaranteed, the height is going to be log n. So whenever we talk about insertion and deletion, it's always log n. So we want to keep this in mind because when we finish the insertion deletion about heap, we're going to go back to the Dijkstra algorithm, assuming that the priority queue is implemented using the heap and see how we can analyze the running time, right? So That's really why I kind of want to interrupt our flow to talk about heap. All right, relational structure. Okay, let's talk about insertion. Okay, so let's now start with this. Okay, let's now go over the steps. Okay, so to really insert a new node, new entry. So, okay, just make sure I'm showing it. Okay, so let's say we want to insert a new entry here. Okay, so this is the new key. And the element here doesn't really matter, just some value. So key is really the thing we want to pay attention to. Okay. Number one, where should we put it, right? Since we want to keep the heap to be still complete and still satisfying the relational property. Let's at least keep it to be complete still. So where should we insert it? The most obvious place is to insert maybe as a new child for this particular node, right? Should it be a right child or left child? Or does it matter? Left child, right? Okay, that one's obvious, okay? Okay, just according to definition. Okay, so step number one. Okay, I'll put it down. So step number one, you want to store the new entry. As the rightmost node at level h, where h is the height. Level h. In this case, you think about level 0, level 1, level 2, level 3. So we're going to store as a leftmost node. Oh, beg your pardon, rightmost node. So I'm going to insert it right here. It's a left child, right? And that one there is going to be 2t. Okay, that's step number one. Okay, we got this new node. So now, as far as the trees, as far as the complete property is concerned, we are fine. It's still complete, but is it still maintaining the relational property? It's not, obviously, right? Because you can see right away, you can see that 2 larger than or equal to 20, false. So that means somehow this 2 here actually happen to be the minimum of the whole tree. Somehow you will have to go up to here, all right? So we're gonna do something called up heap bubbling. Okay, I'm gonna mention the step first, and then we'll see how exactly to do it. Potentially, we have to promote this new entry up, and the worst case, we may have to promote it all the way up to the root if this new key happens to be the new minimum of the whole heap. So we're gonna do something called up heap bubbling. Up heap bubbling. Bubbling in the sense that, you know, if you ever work on bubble sort, we're just gonna keep swapping whenever necessary, okay? Up heap bubbling. And we're gonna see how many swap we may have to do in the worst case, and for each swap, what will be the computational cost? That's something we'll see, okay? I'll leave that a little bit empty just for now. Okay, let's work on exactly this example here, okay? So let's now start with this, okay? So let me start with, first of all, I will compare this new node to, and also its parents. Or you can think about what you're doing is you're naming this particular new node as child, C. Okay, I'm just talking a little bit about like if you want to implement this in Java, you have to create a local variable, C, denoting the child. And the child will have to be keep changing, okay, kept changing as we go, okay? So now this will be C. So what we do, step number 2, we want to check to see whether the child's key will be larger than or equal to the parent's key. That's what we're going to check. So let me just keep writing this. So key of the child larger than or equal to the key of the parents. In this case, the key of the child will be 2. The key of the parents will be 20, right? Apparently, false. So we're going to do a swap. If that's already true, nothing else to do. You basically, the up heap bubbling terminates. Okay, so here we're going to say this is not the case, right? It's false. So that means we're going to do a swap. Okay, so when you do a swap, you're going to say, swap these two. So 2t should become here, and also 20b is here, right? Swap. That's one swap operation. We kind of promote the new entry up. At the same time, you also want to update the child reference if this is swap. So in this case, let me change the color right here. Okay, let's say C, rather than pointing to here, is now going to point to this new node right here. Okay, I'm going to put C here. Meaning that the next step is to compare if the child's key will be larger than or equal to the parent's key, right? That's something we're going to see. All right? So step number 3. So we basically want to check to see if the key of the child larger than or equal to, oh, you know what? Let me just write a little bit better. Let me put a C right here. Leave a little bit more space. Okay, so this is C right here. So I'm checking to see whether, step number 3, okay, whether the key for the child larger than or equal to the key for the parents. Now, in this case, the key of the child is 2. The key of the parents, 6, right? 2 larger than or equal to 6, false, another swap. Okay. So let's say another swap, let me now use pink, okay, just be consistent. So this is another case, we'll do another swap. Okay, you got to be very careful about what you're swapping. So now we are swapping these two. Okay, so now 2t is now here, and also this one will be 6z. Okay. So far you can see now we are not really modifying the structure, but just replacing the node. Structure-wise, it's really the same because it got to remain to be complete. So you can see here we got the bottom node is now here. And the next node is actually right here, right, the orange one. Okay. Okay. At the same time, we should really update the parents. Sorry, the child nodes. So let me just remove this one here. So the next one, let me just do purple. Okay. So now you can think about now this is the new child right here, right? So now we have to now compare the child and also the parents, right? So now it will be number 4. Again, we are checking to see if the key of the child larger than or equal to the key of the parents. The key of the child, again, is 2, right here, and versus 4. 2 larger than or equal to 4, also false. Okay, this time, let me now use orange. Not the case. Okay, we're going to swap once more. Swap these two, all right? So 2t should be here, and also 4c should be here. And now, nowhere to go. That's really the worst case for RP bubbling, in which case the number of swap you're doing is simply proportionate to the height of the tree, right? Okay. So now you can see this is the node here, and also that's the root, okay? So you can think about this is the new root. This is the new minimum after insertion, which makes sense. It's simply 2. And you can double check again yourself to see that at every node, you can see child and also parents, they still satisfy the relational property. All we had to change would be this particular ancestor path for the inserted node. It's guaranteed. It's going to work. All right. Any questions? So 4 steps, okay, proportionate to about the height of the tree. Okay. What will be the running time in general? So you can split that into 2 parts. You got to think about how many levels you have to do the swap. So the number of levels you have to do will be exactly big O of h, the height, which we know is the big O of log n. Guarantee from the structural property, okay? So that'll be the number of levels. For each level, we basically think about what we had to do. Once you get a child reference, you have to do some relational comparison, which is primitive operation. And then after knowing that it's actually false, we had to do a swap, which is about reassigning the references, right? So let's now go for each level. So for each level, we got to basically do some comparison. You got to compare about the child key and also parent key. And also, if they don't really satisfy the relational property, we have to swap. But these two together simply just big O of 1. So overall, the running time is big O of, we got log n levels. Multiply, each level is only about constant amount of time we have to spend on doing the comparison and the swap. So it is simply big O of log n. Okay, overall running time. All right, questions? Yes.
So I think the first or second step, I don't really remember, where like it's obvious visually where we're supposed to put the node, but programmatically, how do we know to put it at that node without having to do a search through the whole?
Oh, you mean the first step?
Yeah.
Okay, it's a very good question here. It's a very good question. There are two ways for you to achieve this. Actually, I think a very common way is you want to always keep a reference about where you are. For example, let's say this, for example. Let's say in the beginning, you have simply this, let's say this. I start with the empty tree and then I got the first node. I will know that in order to really create the next node to insert, this one should be the reference to keep. And then once I got that, I can simply create a left child. Once I have done that, I can now say, I can now keep still keep this reference, and then it can be the right child. Once I have inserted the right child, I should really change this reference to right here, and then keep inserting. You must have a way to really keep, you're trading space for time, to keep the reference to see, that will be the place where you want to insert either left child or right child. Make sense to you? Good, I'll write it down. It's a good question, yep. Now that I mention it, it's a potential place for exam. How about that? Okay, but anyway, it's good to know. Yeah, I wanted to mention that anyway. Okay, so what Josh just said is a very valid point. So for step number 1, programmatically, you want to keep a reference to the node from which the new node should be inserted as a child. Okay, and this one here should only take, we are trading space for time. Trading space for time. Okay, very good. Okay, that should be equal of 1 every time. Yeah?
Doesn't this mean we now also have to run like a update reference function?
So update reference, that means every time you, well, think about, yeah, you got to do that as well. So I think you can think about update reference will be after everything here, plus 1. You only do it once. You don't need to do that for every level. Right? So after the insertion, you want to somehow keep a reference to see where to insert. For example, let's say here, once you have inserted this node, you know that this reference should still be here. Because next time you want to insert a new node, it will be this node's right child. Right? You got to work out a way to see exactly how to update the reference. Mm-hmm. That'll be some implementation detail. We wouldn't worry at this level. Mm-hmm. Question? You're fine. Good. Yeah. Awesome. Good. All right. So that's about insertion. Let's talk, well, also you want to keep it a little bit more general. So here we only talk about insertion where up heap bobbling is actually a good way to go. All right. So not necessarily you only do bobbling, like up heap bobbling when you do insertion. There might be certain scenario where maybe the value you're only changing, for example, if I'm only changing, let's say, this here to be, for example, 3, right? Apparently, the 3 here is smaller than what that used to be. Now, should we do upward or downward? It should be upward in this case, actually, because somehow you want to make sure this 3 here, which is even smaller than this, it should really somehow be promoted up to some appropriate place, right? So you want to keep yourself a little bit flexible. Up heap bobbling is not just for insertion. It could be for other scenario. I'm mentioning this because Dijkstra might have to use this. Okay, I'll write it down. Okay. But up heap bobbling can either up heap or down heap. Always it will take about log n time. Okay. May not be just for insertion. You gotta judge. All right. Good. For example, you'll see Dijkstra. Okay. Okay, we'll see exactly. I'll show you the point where you can see that. All right. So that's about insertion. Let's now do deletion. Very similar, but it's going to be opposite direction that we're going to do the updates. Okay. So let's talk about deletion here. So when you delete a node from the heap, you don't delete an arbitrary node, like how we implemented deletion for a binary search tree. Not the case. When you delete, you're basically saying you want to delete the root or the minimum, right? That's very important to see. So that's why the delete method does not take any arguments. You just say delete, so we will know it's deleting the root. If we want to delete this guy here, right? Let's say we want to do something similar. Rather than worrying about relational property just yet, let's make sure after deletion here, we can still preserve the structural property. So to delete this guy here, we better find some replacement. What would be an appropriate candidate for replacement? It turns out we can just find this guy here, the rightmost node at the bottom level, and put it right here. And of course, as soon as you do this one here, you may have to update a reference for the next node for insertion, right? So this reference should also be updated as well, just in case. Okay, but let's focus on deletion. Okay, so step number one. Step number one would be store the key from the root. Okay, so let's say we store it somewhere. Let's say k here will be some local variable. Let's say k is assigned the value of 4. Let's put it aside, right? We're going to return it at some point. Okay, we're going to store that temporarily. Okay, and then we have to replace the root by the rightmost node at level h. Okay, when I say replace, you got to delete that rightmost node at the same time. Okay, so what we do is we're going to delete this guy here. All right here. Of course, in case the node we want to delete, the rightmost node is only here, in which case you got to delete this one here, and then the heights of the tree is going to be shrink by 1, which is natural. It's possible, right? Just in this case here, it's not the case. Right? So we delete this node here, and then we got to make sure we put that contents right here. So what I will do is I'm just going to put here. It's going to be 13 and W. 13 and W. All right? And as far as the structural property is concerned, the whole binary tree is still a complete binary tree, right? So you go from left to right. However, it's not a heap anymore because the relational property is not the case. For example, you can see that 13 here, compared with its child nodes, is not smaller, right? We have violated the relational property. Now, to restore them, we want to do something that's the opposite to up heap bobbling. We're going to do something called down heap bobbling, okay? From the root all the way down to maybe some leaf in the worst case. So now we're going to do something called down heap bobbling. Okay, so it's going to be taught down heap bobbling. Okay, and then we gotta work out the number of levels, which will be the same, just be go for H, still log in. And also to see at each level, are we doing anything that's more expensive than constant? We're gonna see, okay? Most likely not, but let's see. Okay, and then we'll come back here to see exactly the running time. Okay, so let's now see this. So once you have done the replacement, you can create some local variable. For example, you can see this node here, we can call that maybe the parents. Okay, and then you will see that I'll show you something on the slide very quickly. So RP bubbling, you don't really have to do any decision making for insertion. However, in the case of the deletion, there's one step you gotta watch out. So you can see down here bubbling, right? That's the thing what you're doing now. And then you have, okay, it depends on the shape of the tree. You want to make sure if you got, if the parents you have, okay, for example, let me show to you. Okay. So you want to know which direction should I go for the downhill bubbling, right? So you basically go for the child with smaller key value. Okay. You can think about exactly why it's guaranteed if we simply go for the smaller one, it's not going to break the relational property after the swap. So that'd be some mental exercise for you to think about. Okay, I'll put it down. You can think about it, and we can discuss during the office hour if you need to. But let's not do it. Okay, 5 and 6, smaller child, the child with smaller key, right here. All right. So what we have is, this is a child, right, with a smaller key value. This is a child. And we're now going to actually check the property. Okay, so this will be step number 2. The key of the child larger than or equal to the key of the parents. So here we got 5 and we got 13. Obviously, that's false. Right? So we're going to do a swap. So this is not the case. So we're going to do a swap. Okay? So we are basically going to swap 13 down. Okay? So we're going to swap these two. Okay? So this will be 5A. And this will be 13W. Right now, you can see that this has become the new root. And nicely, 5 is indeed the minimum for the whole tree. So we haven't broken any property. But you can think about why choosing the child with a smaller value should really be able to help us with this. Okay, you can think about that one. So now we're here, right? So now after this, we're going to, again, change the child and parent reference. No parent here and no child here. What used to be the child is now going to be the parents. So let's put the parent here. And now, which one should be the child? 9, right? Because if you compare 9 and 15, right? If you compare 9 and 15, smaller one should be 9, okay? So we're going to go for here. So that's a child, okay? And then, okay, maybe right here. So child should be right here. And then number 3. So again, we say key of the child larger than or equal to the key of the parents, right? Always remind yourself, it doesn't take long to really write this down, so you can plug in the exact number. So the key for the child will be 9. The key for the parents is 13. 9 larger than or equal to 13, false. In that case, I'm going to do another swap. So this is false. So I'm going to do another swap. Okay? So I'm going to swap these two. So 9F should be here. And then 13W should be here. Let me write better. 13W is right here. All right? And we want to do another comparison to see if we should go even further down. And that one there, I'm going to change the parents and the child. What used to be the child is now the parents. And the child, if you agree, should be 12, right? The smaller child, right? The child with a smaller key. So this will now be the child right here, okay? And then we're now going to do number 4. Compare the key of the child Is it larger than or equal to the key of the parents? Compare 12 and 13. So 12 larger than or equal to 13, false. So we're going to do one more swap. So this is also demonstrating a worst case for down heap bobbling. You got to go all the way from root down to a leaf. So this is not the case. So again, we're going to do a swap. Okay. So we're going to swap this and this. So 12H and also 13W. So now since we are at the bottom level here, so we don't need to go any further. All right. Let's just summarize what we have done. Okay. So basically now we have in the new heap, we got 5A, 9F, and 12H, 13W. Everything else stayed the same. We have only modified this particular path. That's all we had to do, nothing else. Okay? We have not modified the structure really. It's a complete, and now everything satisfies the relational property. Okay? All right, so now let's think about the running time. Very similar. See, it seems like at every level, what you're doing here is still constant. It's definitely not anything beyond constant. So we're going to say the number of levels. The number of levels, again, big O of H, because of structural property, big O of log n. Okay, that's what we got about how many times we may have to do the levels. And then for each level, so first of all, we're going to choose the child with a smaller key. So choose the child reference. Okay, that one just about relational comparison, right? Cheap. And also we're going to compare the value of the child, the key value for the child against the key value for the parents. Also comparison. Number 3, we may have to do the swap if the property is violated. Yeah, altogether, 1, 2, 3, still constant. All these will be big O of 1. Okay, so overall, the running time for deletion using down heap bobbling is going to be big O of 1 times log n, right? Each level, and this is how many levels we have. Still big O of log n. Okay, and then, oh, I missed just one step. I'll show to you. Okay, right here. Okay, there's actually one final step because we are trying to delete the root and minimum. So usually the programming convention is when you delete this particular root, you want to return that key value. That's why I kind of said you want to store the key value somewhere in the beginning. So the very final step, which would be number 5. You can think about step number 5. We're going to return the value of k, which is 4. All right. That one, of course, just constant, right? It's not going to change. It's not going to change anything. Everything is going to be dominated by the number of levels in the heap. So the conclusion is for insertion and also deletion, both of them will take big O of log n time, thanks to the structural property for the heap. Okay? And for just extracting the minimum, it's going to be just about reaching to the root, which is constant, right? These are the 3 main operations for the heap. And we can, yeah, I think it's exactly halfway. So why don't we take a very short break? After the break, we're going to apply this knowledge fresh about heap and see how we can analyze the running time for Dijkstra algorithm. All right, let's get your iClicker and then take a short break. All right, so now we are done with this little bit small lecture about heap and priority queue. So you can definitely go through, the written form for the bullet points just to be precise about the steps, which we kind of illustrated using an example. Okay, and that's a summary about the running time. Okay, any questions? Okay, good. Okay, let's now say goodbye to this lecture here. Let's now revisit the graph lecture. So I want to talk about 2 more things about the graph. That'll be the conclusion for your test 2 coverage. Number 1, I want to revisit the Dijkstra algorithm to figure out its running time. And you'll be the most efficient because we just learned about a heap. And then after this, I want to introduce the final way of implementing a graph using matrix 2D array. And then we can do some brief comparison about the running time. Okay, I can do a few examples just to show to you, and then I can leave something for you to give a try. We'll see. Hopefully we have enough time to go over everything. We'll see. So slide number 66 is just one alternative version of the algorithm. So this is consistent with the bullet point that we kind of saw earlier in the slide. So this form here, just a little bit easier for us to really figure out the running time. We'll do that line by line. So we wouldn't really have a chance to implement the Dijkstra algorithm for this course, but now that you know about how to do the edge list in the assignments, and also you know about the principle for adjacency list or adjacency matrix after today, you can easily go beyond this course and implement a graph, and then I try to implement the Dijkstra algorithm using this. You can easily do that, right? You definitely got the basis to implement the algorithm that you want to. Okay, I'll leave that exercise to you. Let's now talk about running time. So I'm going to go over basically slide 67. So we make the following assumption. We are now implementing the capital Q, right? If you remember, so that's the pseudocode version, but I'm going to go over line by line. So we have the capital Q right here. Okay, so this Q here we assume is going to be implemented by a heap. Okay, that's an efficient implementation. Okay, let's remind us about some basic facts about implementation. So let me put it here. So think about the Q here. And let's remind us quickly, right here. So that one there. So we have the priority queue. And we assume that it's implemented by a heap. Implemented by a heap. And the very important structural property is the height is big O of log n. And it's important to draw some connection here because we are trying to put all the vertices into the priority queue. So the n here really corresponds to the number of vertices of the graph, right? So think about this is the input graph that we have, right? We got vertices, we got edges. So this n here really is, at the same time, the number of vertices, right? In the graph or in the tree, right? They are all the same. And then the next one. And we know that to extract the minimum is going to be constant. Just go to the root, right, of the heap to get the vertex with the smallest capital D value. And the insertion and deletion which require up heap bubbling and down heap bubbling. We just spoke about it, a few minutes ago. So that one there is also going to be upper bounded by big O of H, which we know is big O of log n. Okay, so these are just the facts that we learned from the heap, right? So we're gonna keep these in mind, and then we can derive the time, the running time line by line. Okay, so the algorithm, it's okay. Dijkstra shortest path algorithm. You give us an input graph, and we assume that the graph is directed, for example, if you like. It doesn't really matter. So Dijkstra can handle either way. Okay, it can be directed or undirected. And also we get a source vertex to start with. Okay? And of course, this is also assumption, one of the precondition, the weights must be non-negative. Okay? So also we got the input here. I didn't really put it here, but you can just remind yourself the weights for each edge. So the weights should be larger than or equal to 0. Cannot be negative. And the post condition is just about the capital D. Once you have finalized the vertex, meaning that you have already removed it from the priority queue in the current iteration, its capital V value will be the true shortest path, the distance. Okay? And also the shortest path will be exactly the reverse of the ancestor path, which we also talked about when we did the tracing earlier. Right? So that's the output condition. So now we're going to look at the algorithm itself, okay, and figure out the running time. Okay? Most of the lines are rather straightforward, given that we also learned about heap already. There's just a few lines that we had to somehow combine them and to figure out some graph property. And from there, we can figure out running time also straightforwardly. We'll see. Okay? Let's go just in sequence. Okay? You can see just for these 3 lines right here, 7, 8, and 9. Okay? So let me highlight them. 7, 8, and 9. You can see we are basically just making make sure we set the capital D value and also ancestor value little a for all the vertices, right? To be either infinity or 0, and also nil, right? For all the ancestor, right? That's really what 7, 8, and 9 will do. And each set is more like a variable assignments kept like a big O of 1. How many vertices are we doing? N vertices, right? So that's the first one we can figure out. Just for 7, 8, and 9. Right here. You can think about we just got a big O of, we just do variable assignments. How many are we doing? We do for all the vertices. All the vertices will be exactly the number of nodes in the heap. Big O of N. So you can think about we really say big O of V, V would be just N, and also number of edges would just be N. Right? We're going to use these two interchangeably. Okay? It's a reminder, right? That's something we did earlier. Okay, so this part is done. So I'm going to grade it out for now. Okay, just remind ourselves that's something we're going to aggregate at some point later, eventually. Okay? Let's now take a look at this one here. All right. This one is saying we're going to insert all the vertices one by one into the priority queue. In this case, a heap. All right. So now, what should that be? What should be running time? N log n. Okay, that's a very good. That's a good number. How did you figure that should be n log n?
I'm thinking more space where you keep getting the non-ascending and you keep getting the largest value, put it into the heap.
Yeah, you're basically saying for every time you're inserting, you have to do the worst case for the inserting. That'll be the up heap bobbling, right? That'll be log n. And how many up heap bobbling you may have to do corresponding to number of vertices you got to insert, right? Exactly. All right. That's good. So since we talk about insertion, it's going to be big O of log n for each one of them. So this one here is going to be big O of number of vertices. Each insertion is going to cost us, in the worst case, log n for up heap bobbling. Okay. So I'll make some quick notes for you. This log n here is about the up heap bobbling from insertion. All right? Good. So this line here is also good. And let me also grade it out. We're also going to revisit this later. Okay? This is another one. All right? And we don't really count. Number 10 here, we don't really, oh, sorry, not here, beg your pardon. Number 11, right here. This is the header of the for loop, okay? That one there, we're going to use it to really get some insights later. So right here, that's a while loop. Given that right before line number 11, the queue is completely full, in the sense that we got all the vertices in. And we're going to exit from the loop when This negation is not the case, so Q is empty, right? So that means number of iterations should really correspond to the number of vertices in the graph, right? That's also something we said earlier when we traced the Dijkstra algorithm. So this one tells us that the number of iterations will be the number of vertices in the input graph, which will be just n. Oh, for checking to see if the Q is actually empty itself, it's just constant. We don't have to worry about it at this point, okay? Okay, just keep in mind, line number 11 tells us we're gonna execute, basically, this part here for exactly n times. So now we're gonna figure out for each line there, what's gonna be the cost, all right? So line number 12, right here, okay? So line number 12, right here, okay? So that one there, we are simply just really extracting the minimum. Let me just use green. So this one here, we are extracting the minimum. Every time extracting the minimum, now we are only extracting it, we're not deleting it, all right? So now, each extraction of the minimum will take constant time. How many times do we have to extract the minimum? N times, we got n iteration, right? Exactly, good. Okay, hopefully so far just straightforward, right? Okay, so this one here, we're not just calculating this line in isolation. We are saying out of the whole algorithm, iterating for n times, what's going to be the running time? That's what we're doing. We're going to aggregate everything together, right, to make it a bit easier to add up. So this one here is going to be big O of 1 dot times n, big O of n. So you can think about this part here, 1 here, is about extracting the minimum, okay? Extract the minimum, which is the root, okay? And that one there is big O of n, right here, okay? Right here. So now, let's now take a look at the most critical line, right here. So let's now take a look at this line here, line number 13, and also together with line number 11, okay? Let's look at these two together. We want to combine them, all right? So here we talk about how many vertices we have. And this is about each vertex, how many incident edges it has. We actually studied some mathematical property earlier.
So it would be n squared. So let's say we're doing Dijkstra's on.
No, it's cheaper than n squared. Cheaper than n squared. Yes, indeed. Okay, anybody? Let me say that again. We're basically saying we have to figure out for each vertex. And for each vertex, we are talking about only its adjacent vertices. It's not n squared. Cheaper than you thought. It could be in the worst case n squared, yes, but I would say when we first state that, we want to be more accurate because it may not be n squared. Depends on the shape of the graph. It depends.
So if we're,
Not necessarily n squared all the time. It's in the worst case n squared, but we want to get that a little bit later. Okay? Yeah.
maybe n multiplied by the degree of each node.
Yeah, I definitely somehow want to add up the degree for each vertex, right? That's basically what you're going to do. Okay, so here, so let's now only look at these two. Okay, so give me one moment. So here, and also here. Okay, if you look at these two lines, so that one there is actually going to be the sigma of, so since each time we're simply choosing u, right? So u is simply a member of the set of vertices. U is a member of capital V. And then we are saying number of adjacent vertices. adjacent vertices of U. It's about number of incident edges for U. Okay? And that one there is going to be summed up to sigma U member of capital V and also the degree of U. Okay? In the case of the rectangle graph, it's going to sum up to exactly just the number of edges. Okay, so this one here we say directed graph. In the case of undirected graph, you may have a double count, right, for the undirected edge. In that case, there'll be 2 times n, which will be end up to be the same anyway, asymptotically. So this will be directed graph. Okay, so this will be just equal to n. So n value here is one property we learned, and also at the same time what you said there was also not wrong, just not always the case. In the worst case, it could be n squared. When the graph is reasonably complete, the number of edges will be n squared. That's also one of the properties we said. So but I would rather go with m first, and then we say m squared. Right? That's my point. Yeah. Okay. I'll also make a point here, but let's stick with n just for now. Okay. All right. So knowing that, it's going to be basically for this part here, is going to be executed for exactly m times. So that's why I said this is the most important part to really understand. If you simply just want to somehow figure out exactly the iteration, if you try to look at 11 and 13 kind of separately, it's difficult to figure out. But you really want to see the mathematical property here, right? All right, so now we're going to look at the body of the inner loop. Okay, we know that it's going to be executed for exactly m times n. Okay, so let's now box this guy here. All right. And now, stare at this part here for a moment. Only this part. This part here is going to be executed for m times. Overall, what's going to be the running time for this block? Do you think just m? In the worst case. Now let's just stick with n. Let's not worry about n squared. I'll talk about n squared at the end. Okay, just n. So now I'm more talking about each time you try to execute this block of code. What will be the worst case running time? Is it going to be constant or something else? Let me see it again. Okay, guys, be careful. Okay, let me see. It's very important, right? I'm asking this. This block here is going to be executed for m times. Now, for each time I execute this block of code, what's going to be the running time? Do you think it's simply going to be big of 1 or something different? That's a question. You may want to imagine yourself about when you are doing this kind of thing, you may want to modify the vertex, of course, about the capital D value. But remember, what's the purpose of having the capital D? Is this somehow being used for a certain row in a heap? If you change its value, do you have to do something more expensive than you may think to really restore the relational property? I'm giving out the answer. Log n? Good guess, but why do you think it's log n? Okay. All right, so here's the answer. All right. This particular assignment here is telling us we are changing the D value, and D is used as a key value. It will be as if, a little bit like this. For example, if I somehow modify, let's say, maybe this particular node. Let's say there happens to be the vertex I want to update. If I update its value from maybe 9 over here to be 3, for example. In that case, I cannot leave it the way it is. It's not a heap anymore. I may have to do some up-heap bobbling to really go, maybe, possibly all the way until the root. That's kind of the hidden operation you want to watch out for, not exactly explicit. We have to talk about this log n because we're using a heap to update it. All right? Now, think about this point here. It's very important. Okay? So I'm going to write it down. So you want to know that this capital D value here is used as a key. Used as key for the underlying underlying heap. Okay? So this change over here, meaning that we're going to change the capital D to a smaller value. Changing the key to a smaller value requires upheave bubbling to restore the relational property or the heap order property. All right, so I'm just going to highlight just the upheave bubbling here. So overall, this block here, every time you execute, worst case, not constant, log n, because it might trigger some upheave bubbling, maybe every time. All right? So now given this, what should be the overall for this block?
How would the V elements of Q, is that just checking whether it's in the queue, in primary queue, and if so, would the time complexity be constant?
That would be, yeah, that would be some running time, but it's not. It's going to be somehow dominated by the rest anyway. Okay, you're right. So here, when you check to see whether, so this one here. So you're checking to see this one here. This one's interesting. Okay. This one, of course, you got to be careful here because we know that this one here is going to be log n, right? You better do something better than log n to really find out if V is in the queue. So potentially what you can do is you can build some binary search tree about all the nodes you have removed so far and check to see if V is actually the node you have removed already. That can also give you some log n time. You see what I mean? Okay, it's good, actually, yeah. But if you only use a linear array, for example, that's going to be n, in which case you get n times n. You're going to make it even more expensive, okay? I'll write it down. It's very nice you kind of pointed out. So this search operation should not be more expensive than log n. In which case, for example, can we just use a binary search tree? Can we? Or we got to be more careful about binary search tree. Because what's the highest for binary search tree in general? Huh? Should be balanced, right? So maybe I want to go back to the self-balancing binary search tree, right? Okay? Yeah, okay, good. Awesome. You can see lots of consideration here, right? So for example, a balanced, self-balancing, for example, balanced binary search tree. Okay, now you know the details. That's also something we covered earlier. All right, good. Yeah, I really love the question you guys posted. It's really something I didn't really put on my notes. That's good. So this one here is going to be big O of n times log n. All right, and then we're almost done for this one here. Oh, give me one moment. Let me just highlight it first. Question?
For the balanced binary tree, like I get that retrieving a node you can do in log n, but don't we have to build the whole tree, and so that would be more expensive than just?
No, you don't really have to build a whole tree. You talk about the binary search tree we're going to build, right? You can think about a binary search tree initially is empty. So you're going to keep adding. Whenever you want to remove a node from the priority queue, you're going to insert that node into the binary search tree and make sure you kind of restore the balance. You don't need to build it from scratch. You don't have to. Okay? Good. Good. All right, awesome. We got one final line, and then we'll add up everything together, and then we'll make a quick conclusion. Okay? So now, here. Now, at every iteration, we also have to remove the minimum. Well, deletion, we know, log n. How many times do we have to remove? N times, right? Good. Good. So that one there, I'll put it here. Okay? Is going to be big O of n log n. Okay? So now we're going to add up everything together. Right? You can see the way we calculate. We got 1, 2, 3, 4, 5. Right? Somehow, it's going to be dominated by anything with the n log n, m log n, right? Add them up together. That question.
and then the log n refers to that inner block of code. But like, aren't we ignoring the number of times the inner for loop is running?
Not really. We're trying to somehow combine. Because we know that the number of times we're going to execute this block over here really depends on both of these. Right? Agree? Because, okay, so this block here, right here, this is the body of the inner loop, first of all, right? So the number of times this will be run depends on how the loop counter conceptually, there's no loop counter per se, but think about if there are loop counter, exactly we have to think about how the loop counter is going to change between the outer and inner to figure out exactly how many times. So to really do that, we are saying that this one here is going to run for exactly number of vertices time, right, n. And this one here is going to be for every vertex we're considering about its incident edges, which will be its degree. So that's why we're trying to figure out in this way, right? And that one we know is going to boil down, it's going to amount to m.
It's like, I guess I'm not understanding why it's not m.
No, just m. Well, you're really thinking about we're going to say for every vertex, and then for every one of the incident edges for the vertex. In other words, we're covering all the edges. That's what we do. Yeah. So for every vertex, consider its set of all incident edges. That way, we are covering all the edges. Question?
So when you talk about the building the search tree and then the V is an element of the queue, are we able to think about it like the negation, like it is not that it's in the popped queue, like we popped it off and then it's.
Yeah, so that will be more like implementation detail. I'm just saying that. So when you want to support that particular V, like a membership operation there, like a V is a member of queue, you want to be careful. That one there shouldn't be more than log n, because we know that the update operation here is already log n, which is going to trigger some upheave bobbling. So you want to make sure the way you do this one here for membership check should not be more than log n.
Also, it says the queue remove. Isn't it supposed to be log n or is it n log n?
Remove is going to be log n.
Yeah, but it says n log n.
The reason is you can see that, well, just indentation, right? So we don't really remove the queue for every incident edge. We try to remove the queue for every vertex. So just indentation, okay. This is the outer loop, okay? Okay, let me do it again. So this is the outer loop. This is the inner loop. You can see here is these two are outside the inner loop. How many times are we going to execute this? Exactly the number of times we're going to run the outer loop, which will be n times. Which makes sense, because how many vertices are you going to remove from the priority queue? Exactly the number of vertices in your graph.
I mean, yeah, it makes sense, but it's just like, it looks kind of wonky because then the n log n should be n times log n.
Which one? You mean the removal or?
The whole, like, you see, like, the gray one where it's like, O of n times log n should be n times n.
You mean this one here, right?
You want that.
Yeah, well, again, so this one here, again, so to really see exactly how many blocks, how many times this will be executed, right? The way to think about it is like this. You have so many vertices to really gradually remove from the queue, all right? You got so many vertices right here. And then for every vertex, you have to consider the number of edges, the number of incident edges it has. It's really about the number of edges for that particular vertex. And we do have this mathematical property from before. If you try to sum up the degree for every vertex, it's going to be exactly the number of edges.
So yeah, it's just like
It may not be exactly intuitive. That's why I said these are the most important lines to really see. Because if you really go with the normal, just to say, okay, a number of times for the outer times the number of for the inner, it's not that easy to think that way. That's my point. You want to somehow use these two, and then to see how we can translate that into this particular sigma. And then we go back to the property that we learned earlier about a graph. Think about this a little bit more, and maybe I can try to maybe give you some visual, maybe a little bit later. Okay? Question? Yeah, we're gonna move on.
I think they're different, and that's why we use N versus M. But our point is that shouldn't it be like our while loop is our N, so that's our number of elements. Then our inner loop is our M, so that's our number of.
No. Inner loop is not about M. M is about for all the edges, right? Inner loop is about only the incident edges for a particular vertex. They are not the same. Put it this way. This may not be the best visual. I'm thinking on my feet. Okay. So let's say this. Let's say we got something like this. Let's say that's a graph, right? So now we got 3 vertices, and then for this particular vertex, like think about 3 is like an outer loop, right? And then for inner loop, for the first iteration for the outer loop. So here we got 2 incident edges. For second iteration, we got another 2 incident edges. For another iteration, we got another 2 incident edges. When we add up, how many edges have we covered? Exactly 2 times of the number of edges in the graph. But for directed graph, it can be just m. But even if for undirected graph, it's 2m, which will be the same anyway, right? Now intuitive, how about, I know exactly why you guys might be confused. How about this? Think about this a little bit more. Maybe on Friday, I can do a little bit quick visual just to see the graph, just to see how they can be added up. Okay. So after this, we'll try to add up everything together, okay? So we're basically just gonna see n m log n, right? You can do all the simplification, but overall, it's just going to be the running time right here. Big O of n plus n times log n. Is that okay? Because you can see the log n here, we do have to factor either n or n, right? So that's why you say n plus n times log n. That's a factor. I'm pretty sure you haven't seen this before, but there we go, right? Okay. And given this, so this will be the most accurate running time for Dijkstra, worst case. All right, so now let's go a little bit deeper into it, like what you said in the beginning, right? So now remember we also said earlier about another mathematical property. If your graph is reasonably complete, what it says completely complete? In that case, you got number of edges will be just be n squared, right? Okay, so we can rewrite this a little bit if we know the graph is very complete. So now we can now do the following. Okay, so this is really one thing, that's a general form. And now we can transform that into another one, knowing that the graph is complete. Meaning that the number of edges over here will just be n squared. N squared plus n, don't tell me it's n cubed. N squared, right? Okay. So, but however, you cannot really say Dijkstra algorithm will always be n squared log n because it depends on the density of the graph.
Isn't the whole point of Big O for it to be an upper bound?
Well, so that's why I said it's a bit like when you talk about the heights, like a binary search, right? You would say a binary search on a binary search on a binary search tree is big over h. That's the most accurate of saying that because h depends on whether it's balanced or not. It could be log n or can be n. It's similar here. N here is the most accurate of saying how many edges you have. But if the graph is actually more complete, in that case, it's going to be n squared. That's what I meant, right? Okay, yeah. It's a good concern, yeah. Guys, do you mind if I take just 3 more minutes of your time? Okay, just for today, okay? But it's a good question, right? I think that's good. So think about this one here. I try to be very thorough, but you can definitely ask me more, maybe on Friday if you want to. I would suggest the following. Another topic which I want to talk about. which is about adjacency matrix. Okay, this is what I would do. Okay, so adjacency matrix is really the same as before, except, okay, in the vertex level, we are basically introducing some index, okay, about the particular vertex, which can be 0, can be 1, can be 2, and etc. All right, let's look at some visual, okay, very quickly. So now we still got our vertices list. So we still got a linked list of vertices, also a linked list of edges. That's the same as before, okay? And then for each vertex, you can see we got index. We got index 0 for vertex B. We got index 1 for vertex A. Oh, it should be 1. Beg your pardon. And also 2 for index vertex C, right? Sorry, it's a typo. Okay, I'll fix that also later. Okay, so now once we got the indices, so now we got some adjacency matrix right here. Okay, how do we interpret that? Okay, so you can think about this as some matrix, which should be one of the attributes for the graph. Okay, you can think about here, what does it really represent? Let's say for this particular row. Okay. So this part here is really about the matrix at row 1. What does that represent? That one there basically is telling you this, this, and this. So that's exactly the incident edges list for that particular vertex. Okay? So that's the incident edges list for vertex A with index 1. Okay? Before Friday, think about this visualization, right? So the adjacency matrix in some way is similar to adjacency list, because once you get a matrix over here, by given some number for the first dimension, you will be able to get a row. That row over there corresponds to the incident edges list for that particular vertex. Okay? So now this is something I want to mention to you, and I'm going to give you some detailed notes about the running time. In your slides, okay, sorry, I promise 1 final minutes, and then I'll definitely see you on Friday. So if you look at adjacency matrix over here, and take a look at, okay, this table here, it's just about summarizing about all the 3 strategies for implementing graph. It's a very nice table, just to show to you what issue you have for each one of them. I would suggest study this table here, and then go back to the visualization for each one of them. Just make sure you know how they work. And then look at this table here, and try to see if you can convince about the running time. We can go over some of them on Friday. Okay, just make sure you're going to go over that. It wouldn't take me long. It maybe take me about 10 minutes or so. I can go over every one of them still on Friday. But don't wait for me. Please study this. It's going to be covering the test. All right? All right, thank you so much. I'll see you on Friday. Most likely, I think I'll make an hour available for you before the tutorial in my office. I'll announce that in the e-class. Thank you.